All right, here we go again. Another video here for a little review of our basically second-year transformers, but we need to know it for third-year transformers as well. Live from the garage. All right, so now we talked about core losses. Now we're going to talk about copper losses. Last video we talked about core losses. Right there, they're going to always stay the same. The core losses are because of our exciting current. When we take a look at this beautiful transformer that I've drawn up on the board here, our high side and our low side. Let's throw a voltage in there. Okay, I'm going to throw a voltage in here, 120 volts AC. This right here represents the resistance of the coil. Remember that the coil is wraps and wraps and wraps and wraps of copper windings around the core. All copper is going to have a natural resistance. So just to prove that, let's go and have a look at this right here. I'm taking my old school flute meter here. It still works. And I'm going to measure across one of these windings on the low side, and I'm measuring 30.7 ohms. That's a high resistance, but remember, this is a very, very tiny little control transformer. So we're going to go back to the board, and we're going to say that, for our example, we're going to say R of the coil is equal to 1 ohm. Now, copper losses are I square of the load times the resistance of the coil. We're only going to look at the secondary. Same thing's going to happen over on the primary. We are going to have a resistance over there as well. Let's just focus on this. So, right now, I take a look at my three beautiful lights over here. And those lights right now have no switches, are all open. So the current over here in our, in our secondary is 0 amps. So you and I can do that math. 0 squared times 1 is 0. So 0 copper losses right now. So our next thing that we're going to do is we're going to close this switch. When we close that switch, let's say we get some current flowing. Close that right there, and let's say we have 2 amps flowing. That 2 amps is always, remember, current always wants to flow back to the source. So at that moment in time, let's say we have 2 amps flowing that way, 2 amps through right there, and that's going to create some heat, isn't it? So 2 squared times 1, so right there with one switch closed, we're going to have 4 watts. All right, easy enough. So someone goes down the stairs, needs to turn on another light. They turn on that light, let's say another 2 amps flows. Definitely not LEDs. So another 2 amps flows. So I take a look at that. That's going to be 2 squared, total current flowing right here. Let's just do this. It's 4 amps. So now what's our core losses do? 4 squared times 1. 4 times 4 times 1. That's 16. Look at that. The current has doubled, but this has gone up by the square. Our copper losses are going up by the square. So we do one more. Might have to break out the calculator for this calculation. But do another one right here. If we close that, another 2 amps flows. This time, our current total now increases to 6 amps through there, through the core. If we just assume the resistance of the coil is going to stay the same, which we are for our level right now, that goes to 6 squared times 1. Current's gone up again, and look at this. This goes to 36 watts. So things are changing by the square. 2, 4, 6. But look how that has gone up by the square. All right? So copper losses are always going to be changing because of the load. Our core losses stay the same. Good to go. So I'll send you, hopefully that last worksheet with the copper losses is going to make a little bit more sense. There's a big tough question in there with respect to the VA. Thanks, Nathan.